Have you ever wished you could, predict how good a language model will be just by knowing a few numbers?
Like having a magic formula.
Yeah, exactly. Well, researchers are getting pretty close. They're finding these scaling laws that are kind of changing how we think about AI.
It really is mind-blowing how predictable these models are becoming.
So today we're going to do a deep dive into a paper called Scaling Laws for Neural Language Models.
It's a fascinating paper.
Yeah, it's dense, but we'll break down the good stuff. So basically it explains how the performance of these models is measured by this thing called cross-entropy loss.
Which is a way to measure how well a model predicts the next word in a sequence.
Right, so the lower the loss, the better the predictions. And get this, these findings have huge implications for the future of AI. They suggest we can build models that are way more powerful, but also more data efficient.
Which means we can train them on less data.
Exactly, and that could mean faster progress. Plus, we're going to uncover some pretty surprising things about how these models actually, learn.
There are definitely some counterintuitive findings in there.
Okay, so let's get to the juicy stuff. The first big takeaway is that when it comes to language models, generally, bigger is better. The overall scale is kind of more important than the specific architecture.
Imagine you're building a skyscraper. The height matters more than how you arrange the individual floors.
Perfect analogy. But it's not just about making them bigger. It's about these three power laws that basically rule how they perform. They explain how performance scales with model size, which we'll call N, the size of the dataset D, and the compute power you use, that's C.
But there's a catch. There's a diminishing return as you increase any one of those factors alone.
So it's like a recipe, right? You can't just keep adding more flour and expect a better cake.
Exactly. If you want a bigger cake, you need to scale up all the ingredients.
Okay, so to really boost performance, you need to increase the model size, the data, and the compute power altogether. Now, let's talk about overfitting. When a model basically gets too focused on the data it's been trained on and doesn't generalize well.
It's like a student who memorizes the textbook but can't answer a slightly different question on the exam.
Right. And just increasing the model size without enough data can actually make this worse. But here's what's cool. The paper found that this penalty for overfitting is predictable. It's based on this ratio of model size to data size.
Yeah, they figured out a way to quantify the relationship between N and D.
So you can use this to figure out how much more data you need to avoid overfitting if you make your model bigger. Imagine you increase your model size by, say, 8 times. Well, you only need about 5 times more data to avoid serious overfitting.
It's not a one-to-one relationship.
It's like studying for an exam, right? If the material increases, you need to study more, but not proportionally more.
Exactly. And here's another mind-blowing thing. They found that the way these models learn over time, the training curve is also predictable.
Wait, are you saying you can look at the early stages of training and predict the final performance, even if you don't train it all the way?
Yeah, it's like knowing how tall a tree will grow just by looking at it as a sapling.
Whoa, that's crazy. Researchers can get a sense of a model's potential early on.
And decide whether it's even worth continuing the training.
Super valuable insight. Okay, so we've talked about scale, but now let's talk about sample efficiency. This is all about how much data a model needs to learn effectively.
And the fascinating thing is that larger models are actually more sample efficient.
Huh. I would have thought they'd need more data.
That's what makes this so interesting. They actually learn faster and need less data to reach the same performance level.
So bigger models can be more efficient learners.
That's right, and the paper shows this in Figure 2. It illustrates how models with 1 billion parameters need significantly fewer tokens to reach the same level of performance.
Hold on, what are tokens again?
Basically the building blocks of words. So like the sentence, "The quick brown fox" has 5 tokens.
Ah, got it. So bigger models can process less and still achieve the same result. But why is this such a big deal?
It has huge implications for the sustainability of AI. Building bigger models could actually be more sustainable in the long run because they need less training data.
Wow, so less data means potentially more sustainable AI development. That's huge.
And there's one more finding that's even more surprising.
Oh, what's that?
They found that the most compute-efficient way to train these models is to go big on the model size and then actually stop the training early before it's fully converged.
Wait, what? So don't train it all the way.
I know, it sounds counterintuitive.
That's crazy. Why wouldn't you want to train it until it's reached its peak performance?
Right. That's what you'd think, but the data shows that efficiency actually comes from knowing when to stop.
That's a pretty big shift in thinking about AI training.
It definitely challenges the way we traditionally approach it.
So does this mean there's a limit to how good these models can get? Like even with all the data and compute power in the world, is there a ceiling?
That's a great question, and it leads us to one of the most thought-provoking ideas in the paper, the idea of a maximal performance point.
A point where even making the model bigger won't help much.
Exactly. They suggest that there might be a point where we've extracted all the useful information from the language data we have.
So even with infinite resources, there might be a limit to what these models can learn.
That's what the data seems to suggest. They point to figure 15, where the compute scaling law clashes with the data scaling law.
It's like these two forces are pushing against each other, right?
Yeah, and this leads to a really profound question. Could there be a fundamental limit to what language models can learn from the data we have?
Wow, okay, that's a huge question. We're going to need to unpack that in the next part of this deep dive.
So we've got this idea of a maximal performance point where even with like infinite data, the models might hit a ceiling.
Yeah, it's like, how much can you really squeeze out of language data?
Right, and the paper doesn't really answer that, but it definitely makes you think.
What does it even mean to extract all the useful information from language? Like, at what point does language itself become the bottleneck?
That's the million-dollar question, isn't it? Maybe language, as awesome as it is, can't fully capture everything about the world and how we experience it.
I mean, think about it. We use words to describe things, but there's always that gap.
Exactly. Like you can describe a sunset, but words can never truly capture the actual experience.
So maybe that gap is where language models hit their limit.
Right. There might be a whole universe of information that's just beyond the reach of words and sentences.
So what kind of information are we talking about? And how could AI even tap into it if it's not in language?
That's where things get really wild. What if we need to go beyond just analyzing text? What if we need models that can learn from sensory data, like images, sounds, even physical sensations?
Whoa, that's a whole other level.
Right. Like imagine showing a model a video of a busy city street instead of just giving it a written description.
It could learn so much more that way.
Exactly. It could get a sense of the sights, the sounds, the whole vibe of the city. But then there's the challenge of integrating all that sensory data with what it already knows about language.
Yeah, because language is still how we communicate and understand things.
Right. So maybe the key is to find ways to bridge that gap, to develop models that can move fluidly between different kinds of information.
Okay, so we've gone pretty deep on these world models, but let's come back to the scaling laws. We've mainly focused on cross-entropy loss, which measures how well a model predicts the next word.
Right, but language is so much more than that.
Exactly. What about all those other cool things that language does? Like creativity, reasoning, humor?
Are there similar scaling laws for those aspects too?
It's like we've only focused on one tiny piece of the puzzle.
What if we had a model that could not only write grammatically correct text, but also like compose a symphony?
Or solve a complex math problem.
Or write a hilarious stand-up routine?
Those abilities seem so far beyond what current models can do.
They do, but maybe the same principles of scaling apply. Maybe we just need to figure out how to measure and train for those things.
So instead of just predicting the next word, we need to train models on tasks that require them to be original, logical, or even emotionally aware.
Exactly. We need to move beyond basic word prediction and explore the full potential of what these models can do.
And it feels like the paper kind of acknowledges that, right?
Yeah, they make it clear that their focus on predicting loss is just a starting point. There's a whole universe of questions still to be explored.
It's like they're inviting other researchers to join them on this journey, which brings up a big question. What's the end goal of all this research? Is it just about building models that can predict the next word really well? Or is there something more?
I think they're hinting at something much bigger, like a quest to understand the nature of language itself and how AI can truly model it.
It's like cracking the code of language, using these scaling laws as a map.
And if we can do that, it opens up all sorts of amazing possibilities. Imagine AI systems that could help us communicate more effectively, learn languages effortlessly.
Or even create entirely new forms of art and expression.
Exactly. The potential is huge.
Okay, so we've talked about the big picture, but let's get into some of the specifics. The paper has all these equations that describe how model size, data size, and compute power relate to performance.
Don't worry, I won't bombard you with math. We'll just focus on the key takeaways.
Okay, good, because I'm definitely more of a concepts person.
Well, one of the coolest findings is that the amount of data you need to train a model doesn't increase at the same rate as the model size. So as models get bigger, You don't need proportionally more data.
So you can build these massive models without needing mountains of data.
Exactly. It's all about finding that sweet spot between model size and data
And
size.
that makes training these big models a lot more manageable.
Right. And here's another cool thing. The ideal batch size for training changes depending on how well the model is already doing.
So as the model gets better at predicting, you can increase the batch size.
Exactly. And that makes the training process even faster.
So it's like the model learns how to learn more efficiently.
Right. And remember that idea of stopping training early? Well, they actually have a solid reason for that. It turns out that's often the most efficient way to use your computing resources.
So sometimes it's better to stop before you reach peak performance.
Exactly. It all comes down to finding the right balance.
This is all super interesting, but it's important to remember that these are just observations based on the data they had.
Right. We can't just assume these scaling laws will hold true forever. There's still so much we don't know about how these models work.
It feels like we're just scratching the surface of what's possible.
Absolutely. But the progress we've made is pretty mind-blowing.
It really is a crazy, exciting time to be in the AI world.
Okay, so before we wrap up this deep dive, let's circle back to one of the most fascinating ideas from the paper. These world models that the models might be building.
It's like they're creating their own virtual realities inside their digital minds.
And those world models could have a huge impact on how these models understand and interact with the world.
Imagine a model that can reason about the world, make inferences, even plan actions, all based on its internal representation.
It would be a huge step toward true artificial general intelligence.
Okay, but how does a language model go from processing text to building this complex world model?
Well, think about it. Language is basically a way of encoding information about the world, right? We use words to describe objects, actions, relationships, all sorts of things.
So by processing tons of text, these models are indirectly absorbing information about the world.
Exactly. It's like piecing together a giant puzzle.
And the more pieces they have, the clearer the picture becomes.
Right. And as that picture gets clearer, they can start making connections and inferences that go beyond the specific data they were trained on.
Wow, that's pretty incredible. But if these models are learning about the world through language, does that mean they're also inheriting all our biases?
That's a super important point. Language is definitely not neutral. The data we feed these models will shape how they see the world.
So if we train them on biased data, we're going to end up with biased AI.
Unfortunately, yes. That's why it's so crucial to be super careful about the data we use and to constantly check for bias in these models.
We need to make sure that the world models they create are as fair and representative as possible.
Absolutely. But even if we can solve the bias problem, there's still a bigger question. How accurate are these world models anyway? I mean, they're built from language, which is a human invention. So are they just reflecting our own limited understanding of the world?
That's a good question. What if there are aspects of the world that are just too complex or nuanced to capture in words?
Right. Maybe there are limits to what these models can truly understand simply because language itself is limited.
So where does that leave us? What does it mean for the future of AI if there are things it just can't learn from language?
Well, it doesn't mean we should give up on AI. It just means we need to be realistic about its capabilities and keep exploring new approaches.
Maybe we need to find ways to teach AI that don't rely so heavily on language.
That's definitely a possibility. But even if we stick with language models, there's still so much we can do.
We can experiment with new architectures, try different training methods, and find new and creative ways to use these models.
Exactly. And who knows what amazing discoveries we'll make along the way.
So we've got these language models, and they might be building their own little world models inside their digital brains just by crunching tons of text.
It's a wild idea, right? Like they're creating their own virtual realities.
But it makes you wonder, are we kind of limiting them by only feeding them language? What if we could give them access to other kinds of information too? Like what if we could show them images, play them sounds, or even like simulate physical sensations?
Wow, yeah. It's like we could give them new senses, right? Let them experience the world in a much richer way.
Imagine showing a language model, a video of a busy city street, instead of just giving it a written description.
Exactly. It could learn so much more about what it's like to actually be in a city. The sights, the sounds, the whole vibe.
It could be a total game changer for how these models understand the world.
But then there's the challenge of like, how do you actually integrate all that sensory information with what the model already knows about language?
Right, because at the end of the day, language is still our main way of communicating and understanding the world.
So maybe the key is to find ways to bridge that gap,
Hmm.
to develop models that can move smoothly between different types of information.
So we've talked a lot about these world models, but let's zoom out for a second and think about those scaling laws again.
Right. Those laws that tell us how well these models perform based on things like size and data.
And one of the big takeaways is that bigger models tend to do better, but there might be a limit to how much they can improve, even with all the data in the world.
Yeah, which raises some interesting questions about how we should actually be building these models.
Exactly. Like, if there's a ceiling to how good they can get, does it always make sense to go for the biggest, most complex model?
It's definitely something to think about. Maybe instead of always aiming for the biggest model, we should focus on building more specialized models, each designed for a specific task.
Kind of like having a toolbox with different tools for different jobs.
Exactly. You wouldn't use a hammer to screw in a light
Right.
bulb, right?
So maybe instead of one giant do-it-all language model, it makes more sense to have a bunch of smaller, more specialized models.
Yeah.
Like a model for writing poetry, a model for translating languages, a model for summarizing scientific papers, and so on.
I like that, a toolbox of AI. And it could even help us address some of those concerns about bias in these
Oh,
models.
how so?
Well, if you have a model that's specifically trained for a certain task or domain, you can be more intentional about the data you use to train it.
So you can make sure that the data is representative and fair, and that the model isn't picking up any harmful biases.
Exactly. It's about moving away from that one-size-fits-all approach and embracing the power of specialization.
This has been such a mind-blowing deep dive. It really feels like we're just at the beginning of something incredible with these language models.
It's a super exciting time to be following this field. And even though there might be some limits to what these models can do, the possibilities still seem endless.
We've learned so much, like how bigger isn't always better, that language might not be able to capture everything about the world, and that specialization could be the key to unlocking even more potential in these models.
And who knows what amazing discoveries are waiting for us just around the corner.
If you're as fascinated by all this as we are, we highly recommend checking out the research paper we talked about today. It's definitely a tough read, but it's worth the effort.
And don't forget to join the conversation on our social media. We'd love to hear your thoughts on the future of language models and all the big questions we've explored.
Thanks for joining us on this deep dive. Until next time, keep exploring, keep learning, and keep asking those big questions.